Welcome back, friends. We are into ninth module of AI. We'll be discussing about neural networks this time. We have looked at a few problems and the method of using state space search in solving them. Those problems were quite structured in the sense that we can define something called a start state, something called an end state. We can define state space and we can define rules which can let us move around in state space, moving from start state to the end state. In some cases, it is not possible. For example, if you want to recognize a signature, the problem itself is quite fuzzy. Not only the problem is fuzzy, though we are able to effectively solve that problem, we will be able to recognize a signature, we will not be able to tell exactly how we have done it. So, that is the first thing, the no algorithm issue. You meet your friend after many years and he is grown in all dimensions, but you still be able to recognize him. How have you done it? It's again is something that you cannot explain. There is no algorithm that you can talk about. That's the problem. Here we can change this, we can actually mimic this by changing the program itself, the way we code. How it is done in a lot of long back in 60s, computer scientists who were working on such problems understood that these problems are different. They are not similar problems. A human brain can easily do it. It can deal with these incomplete fuzzy things and so on and so forth, but conventional computer programs couldn't do it. So they thought that let us try to see how human brain does it, and they worked on it, and they try to mimic the working or functioning of human brain into computer programs. What they try to do is they try to learn the neurons, how the neurons of brains are functioning, and try to mimic the very neuron in the computer domain, that is called artificial neuron. And using artificial neuron, they try to solve those seemingly complicated problems. I use word seemingly complicated because recognizing a signature is not a great job. You probably a very low intelligent person can also do that. It does not seem to be all that complicated. Looking from only the programming perspective, it's pretty complicated. Otherwise, it is not all that complicated. So the point is, researchers started working in the direction of designing or mimicking human brain by providing algorithms which can work that way. And there are many models. In fact, a lot of people came out with a lot of models, and there are plenty of models that exist in literature. What we are going to talk about is preliminary, few basic things about neural networks. Once they do it, once they are able to mimic the human brain, they are able to do many other things. They are able to solve some problems unsolvable for years. Even today it is being so. It is able to solve a lot of problems. For example, recently Google provided a solution. You just look at the image and can ask for something which is otherwise just impossible. You can ask for the color of the tail of the cat, or ask for the hat the tennis player is wearing, and the computer program looking at the image can answer you. No, such programs were just impossible a few years back. This is because of a lot of advancement in this particular field, these neural networks. So in this particular module, we'll be discussing about what neural networks are. In subsequent two more modules, we'll be looking at one or two very powerful algorithms of using neural networks. Okay. It's a separate discipline today. Neural network is come out of AI, is no longer a part of AI actually, but still people talk about neural network when they talk about AI. Neural network has become a discipline on its own. And there are a lot of problems like recognizing a face, recognizing a signature. Interestingly, two of my students implemented neural networks for very different cases. One particular student implemented this to shortlist a resume. In his company, there are 5,000 odd resumes coming in daily. And what they need are a bunch of experts who could look at those resumes and filter people whom they can interview. And it's a expensive process because experts will have to look at all those resumes. What he did, he wrote an artificial intelligence program based on neural networks, and when he could do it, the advantage of that program is that could shortlist those 5,000 resumes into just 500, and experts' work is reduced tenfold. Okay, they could concentrate more on better resumes, and it could result into far better shortlisting process. So that's one example. The other example is one more of my student who used neural networks to find out base set of motivational strategies for employees. I'll be talking about that in due course. Basically, what we want in neural network solution is to mimic human brain. This brain is very different than computer. The computer processor, and now we will be discussing about the differences between these two. Looking at the differences, probably we will have some idea what is different in computer artificial neuron in the brain compared to the processors, and you will learn about the motivation for having the artificial neuron. The first difference is that the neuron is very slow. It operates in the range of milliseconds. Our processors operate in range of nanoseconds. So, there is no match here. Neuron is very tiny thing, and it uses electrochemical reactions, okay, the signaling process to send and receive. Here the computers use electromagnetic waves, you know. Neurons memory is pretty less, it store very few things. There are total 10^10 neurons in the brain and total 10^14 interconnections. That mean there are almost 1000 connections from a neuron to other neurons. And these connections are dynamic, they change over a period of time, and these connections are weighted, they contain weights, and this weights basically carries the knowledge that we have in our brain. Point is a huge distributed, interconnected, dynamic structure. The structure is not only dynamic, the structure is also completely distributed. Every neuron takes a decision on its own, others don't take decision on its behalf. There is no central authority, unlike computer processors. It is completely distributed and all neurons work in parallel, and it is quite fault tolerant, the sense that our neurons are constantly dying. Since birth, the neurons don't remain there steady living, they are constantly dying, but we don't lose important information there in our mind, okay. The beauty is that it stores information in distributed fashion and not a localized fashion like computer programs. So, we will never have that data loss kind of an issue. Sometimes somebody do have, but usually our brains are capable of making sure even if the neurons die, they don't lose data. Okay, so that's something which is very different from a computer program, computer system, and human brain. One more thing is that it's capable of looking at fuzzy things and manage. We are looking at a cricket match, and you see a side face of a friend, and you recognize him. You are able to work with a partial information. You have incomplete information. You've been to a place long back and now you visiting again. You don't have complete information about the current status, but you will soon be able to find your own way out based on the old memories, little part of something that you can remember. So, the idea is that the brain is capable to manage fuzzy and incomplete information. The design itself is in that fashion, and they work in complete sync. The neurons never have any issues of synchronization. Unlike that, however fast these processors are, and number of processors can also be much larger than neurons, the issue is synchronization. Scientists have not yet found a way to sync those processors in a seamless way. So, people are working on it, but there is no solution yet. Obviously, there are no algorithms here. Brain solves many problems without algorithms. Recognizing somebody is one example. Hearing few bars of music and recollecting the entire song is the other. There are many similar things. Or search in an associative way is one more. For example, I say that there was a movie where Shah Rukh Khan and Deepika was there, and the Parsi actor also was there. I won't name Bowman, but I just say that there was a Parsi actor, and you would immediately come back and tell me it was Dilwale. Now, how did you do that? Oh, no, sorry, it's Happy New Year. So, how have you done that? You did that because you could associate this information and search in associative way. We have talked about this in past. So, this associative search is also something where human brains are far better compared to us, the computers. As I said, researchers tried to mimic brain. So, the first thing that they wanted to do is to have a neuron which they call artificial neuron. Okay, so there are many researchers developed many artificial neurons. So, we are not going to discuss all of them. We are just going to talk about the most preliminary. First of all, let us look at the basic brain neuron. Okay, basic brain neuron is roughly divided into three parts. One is called dendrites, which is basically an input device. It's something which provides input to the cell, the nucleus of the neuron, which has a long cord which is called axon, and which again it is distributed in small tiny threads. Okay, so this axon is basically an output device. So whenever an electrochemical signal arrives at a neuron, the dendrites will capture that, send that thing to the nucleus processes that and then send it across over axon. Axon connects itself to dendrites of other neurons, and as I said, such connections are plenty, on an average 1000 connections. So every neuron on an average is connected to 1000 other neurons. It's a huge network and highly connected network. Okay, so this is the artificial neuron also is designed exactly in that fashion. So you can look at the next slide. What does this artificial neuron do? The nucleus job is done by a function called sigma. Okay, there are sometimes other functions used. We'll be looking at few other functions in due course, but the sigma is basically summing up everything that comes in. Now remember, brain uses a stimuli, some information that is coming in, plus weight. Okay, so here also we have inputs, the inputs are x1 to xn, and there are weights are w1 to wn. Okay, so and sometimes an additional value is provided. In the slide you will see that there is an additional value 1 which is provided, w1 1, w2 1, w3 1, wn 1. Now you may be surprised what that 1 is. 1 is called layer. Many a times the neurons appear in multiple layers. So this value describes weight of which layer. Okay, so we'll come across this once again. Some authors describe the layer at the end, some authors describe the layer in the beginning. So you can write this thing as w11, w12, w13 and w1 and so on. That also is perfectly valid, because that also is acceptable in literature. The sigma does what? It just sums up things. So every line has two components, xi and wi. So it just multiplies xi wi, x1 w1, x2 w2, x3 w3. At this point of time I am not bothered about layers, so I am just writing it that way. So it's basically sigma xi wi, where I ranges from 1 to n. That's the first thing. And you can see the row, the next one, the row value. That row value is basically a function which checks for a threshold value. If the summation is beyond a threshold value, a typical threshold value, it outputs 1, otherwise it outputs 0. Now, it's a very simple function. It outputs 0 or 1 based on the total summation of wi xi. So wi xi is going beyond a point, you output 1, otherwise you output 0. So that is this function. So the artificial neuron, you can see that it is pretty simple design. The next slide talks about the same. You can see that the first line says x1 w1 k, x2 w2 k. Now here k again is a layer which I was talking about. K also can be there in the beginning. Okay, the subscripts that we are using here 1 to n. Okay, the subscript order is the designer's choice. There is no fixed rule. Okay, now interestingly, when you start doing it this way, there can be 3 different types of outputs. Now what are those types? The first thing, for an input, for example, I am taking a very simple case of recognizing an image. So what I do is I provide images of 5 different friends of mine, and I want the this neuron to learn to classify them. So I just provide those images as inputs to my neuron, and those inputs, and I pick up some random weights. Those weights are multiplied with the inputs and the summation is generated. Okay, let us take a simpler case of having just one employee, one friend. So the output is whether it is the friend's image or not. So we'll have only 2 different types of images of the friend that we would like to recognize and some other images. So only 2 things. So that simplifies our description. So when this happens, it is quite possible, there are 3 possible outcomes. One outcome is that I provide image of the friend and it recognizes it correctly. So for example, I assume that for correct image the output should be 1 and I get 1. So that means great, this person is recognized clearly. But then there are 2 issues. One, I may provide the image of my friend, but the output says he is not. Image of some other object is provided and it says it is the friend. Now here please understand, there are 2 different problems. Both of them are misclassification. In case number 1, we say that it is the summation is beyond greater than the threshold value, there is a problem. Okay, greater than the threshold value, it's a friend, but we provide something else and still the summation is beyond that. So, that is called positive misclassification. Okay. The other way around, if you provide the friend's image and the summation is less than what is expected, is called negative misclassification. Okay. So, classification can be only one, correct classification, right image, friend's image says friends, non-friend says non-friend, great. But then if you provide friend's image, it should say friend and it says the other one, and when the other one is provided, it says friend. These are the examples of misclassification. Okay. There is one more thing, the row which we discussed. In fact, we can assume it to be part of summation. It's again very simple. What we are doing is x1 w1 plus x2 w2, x3 w3 and so on. We can say that this row, we call it w0. So, it is basically, and we can take it on the left side of the equation. What we have is x1 w1, x2 w2 at the end minus w0, greater than 0, then it is firing, less than 0 it is not firing, or output 1 or 0. We also have x0, assume x0 as 1 and w is minus, w0 is minus threshold. Then the equation is very simplified. It is x0 w0 plus x1 w1 and so on, and it is greater than 0, then fires, less than 0 it doesn't. Now, this is simplified version of the very function. Remember, x0 is not an input, it is a value 1 and w0 is minus threshold value. Okay, this function is known as an activation function. The first activation function that we look at is called square, which we have already seen. The square function is sigma equal to 0 to n x I y I. If it is greater than 0, it fires, less than 0, it doesn't. Okay, it's very simple. If you draw a graph of it, you will be able to see that is basically square. I will just see that soon. The next one is called sigmoid. Now, that is little different function. The same summation is calculated, but then what you have is 1 upon 1 plus e raised to minus sum. You just calculate it that way. Is there shown on the screen that you better see that yourself. Okay. So, this is called sigmoid function. Physically, the square function look the same as shown on the slide. The next slide talks about the shape of the square function. Okay. Why it is called, you can see why it is called square. It is like this. Okay. It is basically a discrete function. For all negative values it is 0, for all positive values it is plus 1. In fact, the vertical line that you see from 0 to 1 is not actually indicating any input. It is just shown to make sure that it looks like square. The sigmoid function you can see is S shaped. When you approach minus infinity, it becomes 0. When you approach positive infinity, it approaches 1. Okay. That is sigmoid function, which you can see drawn on the second slide. Okay. The first one is a discrete function. You can see that the second one is not discrete, it is continuous. Some algorithms which we are going to study later requires this function to be continuous. Okay. So, where sigmoid function is to be used. Square function is pretty simple. It just sum things up and just check for the threshold or 0 value. It is pretty simple and can also be used in embedded devices, IoT devices and many other devices which does not have the power or computation power or memory to process all this. Okay. It is also used in satellites by ISRO scientists, because again over there is an issue about power as well as this thing. So, they innovatively used this thing. They are not using square function as it is, they are doing something else. Sigmoid, because it is continuous, it is possible to differentiate, and differentiation is very required. Why it is required? Sorry, I cannot talk about right now. If you look at the mathematical background of some algorithms like backpropagation, you probably will be able to understand why differentiation is a must, but understand that this is a very critical requirement for a function to be used in backpropagation like algorithm. Backpropagation algorithm is something which is used to train neural networks. We will be looking at that algorithm in the next module. An interesting thing is, if you look at the shape of both functions, if positively classified, correctly classified value, for example, for your friend the output should be greater than 0 and you get 0.1. Now, is it a good thing to have? It is not very good, because if later the weights would change later, this value might become negative. What we want is, we want a much larger value. The summation should be beyond, it should be far from 0 in a way that later on if some weights are reduced, it will still be more. So, it will still be able to recognize that image as your friend. So, you need to increase summation even for correct answers. Why here it is not possible in square. In sigmoid will continuously increase, because if you want to get 1, actually it is sigmoid will output value between 0 and 1. If you want to get 1, you will have to get the summation should be positive infinity, which is very hard, almost impossible to get. Similarly, if you want to get 0, you will have to get negative infinity, which is also impossible. So, it continues to learn even if it has learned that thing correctly. Most of the cases, what we do is we provide a cap, say that when it reaches 90%, 9.9, we accept that thing, or minus 0.1, then you accept that thing as valid. Instead of 0, we accept 0.1, instead of 1, we accept 0.9, just because of this problem. And it is also called tolerance level. So, a tolerance level is 0.1. What is the learning? I just said a few times a process of, let's say this is a process of learning. What exactly is a process? Okay, learning is a process which for getting such a weight which can identify every input as correctly, but we don't know what those weights are. So, what we do is we begin with random set of weights and somehow make sure that these weights are changed over a period of time and converge into the set which gives us the right combination, right answer for every input that we provide. How it is done? In fact, it is done, I talked about friend, now I can talk about something similar called recognizing faces of employees of a company. Okay, so you provide those employees, 20, 30 employees, and their 50 odd images of each one of them is fed into the system, and if it recognizes, it is fine. If it does not recognize, you will have to change those weights. Okay, so if it does not recognize, you just continuously change those weights. Eventually, it will converge into that set. And you may ask me, if you ask me what's the guarantee that you have, let me tell you, there is no theoretical guarantee of this process, but empirically it is proved that in most cases you get them. So, that is it. What we do is we just get all those images, store those images in the database, provide each image to the algorithm, we call it neural network algorithm, backpropagation neural network, or some other algorithm. After every input, we adjust weights, and once we provide all inputs, all employees, all images, 20 employees, 50 images of each one of them, 1000 total images, all of them are fed in. Once they are done, weights are adjusted, one epoch is said to be over, and you will have to do it again, second epoch, third epoch. In normal cases, you require 25,000-30,000 epochs, and sometimes you need to have more number of epochs depending on the complexities of the images that you provide. You will have to continue doing it unless and until you get the final result. But remember, what we need to do is what we need to do for positively misclassified and negatively misclassified. Remember the idea. In case of positively misclassified case, what has happened? The summation should be less than 0, but it is going above 0. You will have to reduce the summation. You cannot change x size because that is the input, that is the image that is coming in. You cannot change that. You can only change the weights. And again, input is of two types, 0 and 1. Okay, those bits are what? 0 and 1. So, anything multiplied by 0 will be 0. So, xi wi case, all xi's where the xi value is 0, wi does not make any contribution to the summation. So, what we have to do is wherever the xi is non-zero, 1, we will have to change the value of w. We will have to reduce that value because we want to reduce the amount of summation. But the answer is that what we do is we will reduce the weights of every case where xi is non-zero. Hopefully, the summation will be less than 0 now. Similarly, when you have negative misclassification, it is the images of your friend and it is not saying yes, then we will have to increase the amount of summation. Again, anything multiplied by 0 is not contributing. So, we will only increase, now we are increase the weights associated with all non-zero inputs. So, that is what we are going to do in learning process. We have already seen that even correctly classified inputs are also learning in case of sigmoid. For square, it is not. Okay. The default form of square does not actually do it. The slope of an activation function also is an important thing here, because if you see that slope, okay, now if you increase the summation, the value is available on the y axis. Larger the summation, higher the value, more the value. Look at the sigmoid function, you will be able to see. You take the summation further and the value is more. So, it will continue increasing it, you will get a better value. If the slope is like this, if slope is more steep than the earlier case, little change in the weight will increase the output much further. So, it learns faster. What the point here is that you can decide that slope of an activation function for if you want to learn faster and all that. Okay, so that slope can be adjusted. Okay, learning faster is not always advisable. So, but you may ask, let us keep it like this, so it will immediately bump up and learn. No, that is not a very good idea. Usually, it is little 45 degrees. Okay, is most common case, but you can change that slope here and there to improve the speed and let the algorithm solve the problem in faster. Sometimes that is needed. Okay. The other thing, how many samples do I need? In fact, I just said that for 20 employees, each of the employees I have 50 images. Now, how have I decided those 50 images? There is no thumb rule for it. People have done research and people have worked on it, and the rough relation is that more complex the figure is, you require more learning. Okay. So, more number of samples. Ideally, the sample should contain everything that could be there. For example, if my signature is to be recognized and I'll have to actually try writing my signature 20, 30, 40, 50 times, and hopefully it should cover all different variations I produce while I sign. Okay. Once that is done, we will be able to recognize my signature much more correctly. Okay. So, that is how it is done. But then there is one more important issue. The neural network should not only recognize my system, my signature, but should which I already presented, or should not only recognize the image which is presented in the database, but should also be able to recognize some other image of the same person, and that is called generalization. And this is something which is there in humans as well. If you teach a student how to draw A and recognize A, any sized A he should be able to recognize later. So, that is called generalization, and we expect artificial neural networks to exhibit that characteristic. And in fact, this method, though we have not yet specified how it is, so we will look it later, it is possible to generalize. In fact, this method is good enough for us to generalize. And this process is like black box. The system works like a black box. The inputs are provided, outputs are generated, and we correct those outputs by changing these weights. We don't really know how these weights encode the knowledge, but somehow at the end these weights are able to recognize signature, finding out who the person is in the image and so on and so forth. They are able to do it, but the knowledge, we don't really know how it is being done, because it is encoded in form of weights. That is why it is called the black box of reasoning. Our brain somehow, and brain also works that way, it stores that information in some convenient form which is not known to any one of us. Okay. Most of the vision and audio related information is stored that way. In fact, there is one more important type of learning which is left. So far, we have said that we provide input, we say that this is the right output. If the program generate a wrong output, we convert that, we change weights to make sure it generates the right output. Not always we learn that way. Okay. Many a times we look at things and classify them. For example, we look at essays and decide that this is a good essay and this is a bad essay. We meet people and decide this is a good person, this is a bad person, this is not so nice person, and so on and so forth. How do we do that? We look at their characteristics and somehow relate people with similar characteristics together and then group them together. That grouping or clustering of inputs also is very important. That also is type of learning. That is called unsupervised learning. Okay. Unsupervised because you don't have any feedback. You just do it on your own. Okay. There is no feedback whether this is right or wrong. In case of supervised learning, what you provide, for example, given an image of an employee of a company and it produces that this guy is Ram and is not Ram, is Shyam, should be able to tell and should be able to change the weight in a way that next time the same image is provided, it should say it is Ram and not Shyam. That is not happening here. Okay, that is why this is called unsupervised learning, which is also quite important. And many a times this unsupervised learning is as a process, pre-process for the supervised learning. With that, we will come to an end of this module. What we have seen in this module, we have introduced neural networks in this module. We have seen how brains work, the artificial neuron, and then we have looked at how this artificial neuron actually can process data. We have seen how threshold value can also be used together with the other inputs, and we have seen two activation functions, square and sigmoid, and we have seen why a function like sigmoid is used in some of the algorithms that a neural network is using. With that, we will conclude. Thank you.